Let me recall what we did last time. So, the Banach algebra, the Banach space and the algebra such that it satisfies the inequality, Banach inequality. Then we defined for a x in A, we defined the spectrum sigma x, which is a non-empty compact subset. Compact subset. Then we define the spectral radius R of x equal to mod lambda supremum. Mod lambda, lambda n sigma of x. Then we proved the formula, which is called spectral radius formula. It is R of x equal to norm x power n this limit. This limit exists and it is equal to the spectral radius. We proved this. So now we consider the Banach algebra B of h. Yeah, you are asking something? No. Okay. So now let we consider, there is a problem of defining this inverse with respect to the algebra, whether the inverse exists in this algebra or a bigger algebra and all that. But we will, for us, we consider when we say T, sigma depends on the invertibility, So for us, when we say invertible, for operators, it is invertible as operators. That is, it is invertible in B of h. This is equivalent to it's invertible in B of h. So when we have unit, identity is that in the C-star algebra. We can talk about Banach algebra containing in A, containing in B of h. Okay. Something is invertible in B of h need not be the case that usually need not be invertible in A. But when we assume the unit is, the identity is same, this may have a different identity. If it is a subspace or something, maybe you can project it or something. Okay, so we assume when that is the case, we are not proving it, but this sigma x is, well defined. If you want, you take it as sigma x with respect to this Banach algebra, or we take the definition of the operator. There's a spectrum for an operator. Okay, so let T in B of h. So let me write it as a proposition. In Banach algebra, we will define C-star algebra. In Banach algebra, there is a problem of sigma, how you define the sigma. It depends on the algebra or subalgebra. In C-star algebra, that problem is not there. If it is invertible with respect to the big algebra, it's invertible. The inverse is there in the subalgebra also. One can prove it, but we will not require that here. We will use this proposition. This is for a normal operator. It's normal. Then norm of T square is equal to norm T square. We will prove this. For the corollary is, so now it's a normal operator. So it has, you can talk, we talk about the spectrum and the spectral radius R of T. It looks like gamma. R of T. This is equal to, of course, the limit exists, so you can take any subsequence. So T power 2n power 1 by 2. We can take this. Right? T power n 1 by n. Instead, we can take it like this. So which is equal to limit, which is equal to norm T. That's all. If this is satisfied. Norm T square equal to norm T square. So T power T square, T power 4. Everything is normal. T square is also normal. T power 2n is normal. So you can take it out, the 2 power n out. So this is equal to norm T. So for a normal operator, this corollary is for a normal operator, spectral radius is same as its norm. Now we prove this for the normal operator. Proof of the proposition. So norm T square is, we have seen that we observed T is normal is equivalent to norm Tx equal to norm T star x. Norm T star x for all x. I mean, these are all operators. We are working with operators. So we have seen this because of the norm t square equal to supremum of norm x less than or equal to 1, norm of t square x. Right? Now t square x is t of tx, so you can insert a t star there, right? Since t is normal, this is less than or equal to norm x less than or equal to norm of t star t x. And this is equal to norm t square. I mean, this is t star tx, which is equal to norm t star t. This is equal to norm t square. Right? So norm t square equal to, I mean, norm of t square equal to norm t square. I just, instead of t, I put a t star because this is true for all x. It's particular for tx, so I have just inserted. So if t is normal, then this is true. Because of that, we got this crucial equality that r of t, the spectral radius of t, is the same as norm of. Okay. Now we want to prove something called spectral mapping theorem. This is for any Banach algebra you can do. That and we want to use this to get some representation for, I'll come to that, C of for a corresponding to a self-adjoint operator. So proposition, let's take a Banach algebra. P be any polynomial. It's a complex polynomial. It's complex polynomial. Then, so A is a Banach algebra, P be a polynomial with complex coefficient. Then I want to say that. So once you have a polynomial, so if you have an operator t, t square, all those things exist. So if you have a polynomial, p of t exists. It's just an algebraic equation, so you can talk about p of t. So sigma of p of t, you can talk about. Okay. P of t is an operator. Sigma of p of t, you can talk about, which is same as p of sigma of. We have proved this inclusion for an analytic function earlier, but for polynomials, this is the equality holds. Okay. Even we will later prove it for continuous functions and even measurable functions. Okay. When, I mean, for a nice operator, for a normal operator. Okay. So if it is a polynomial, here you don't even need star structure. It's just a Banach algebra, and then this is true. So proof. Of course, if polynomial is constant, there is nothing to prove. I mean, if it is a constant, then this is just going to be a singleton constant, and this will also be singleton. P of some polynomial of something is also the range is constant. So let P is not equal to constant. Let P be non-constant polynomial, and it's a complex polynomial. So there exists roots. I mean, so let P is equal to some constant times some k times P equal to 1 to n P of z equal to z minus zi lambda. Okay. We can write it like this because it's complex polynomial for lambda 1. So these are these are the roots. You can repeat it n times. Okay. I talk about for lambda. Let lambda be in P of sigma of P of t. Okay. Let P of z minus lambda. This is also a polynomial. Right. I take a lambda. I want to prove this equality. I take a lambda in sigma of P of t. Then I want to show that lambda is in P of sigma t. There exists some other complex number such that P of that complex number, I mean, where complex number belongs to this sigma of T, and that is equal to P of that complex number. I want to prove this, right? Sigma of P of T equal to P of sigma T. Okay. I take a, no, sorry, I'm sorry to change this. I mean, actually, I want to argue it for the complement. Right. So let it be. So I want to use the, I mean, I want to use the fact that if you have commuting elements, n commuting elements, then the product is invertible if and only if all of them are invertible. Right? If the product is invertible, then you take any one factor, okay, then you can multiply with all the other factors, the inverse, you get this inverse of this. Right? So let me write it. So I'm just taking some lambda. Okay, lambda is in complex, it will be complex number. Okay, then P of Z minus lambda looks like this. Okay, those are the roots, lambda 1 up to lambda n. Okay. So this implies, of course, P of T minus lambda equal to K into the same thing holds. Okay? T minus lambda. This is true, of course, for any T, this is true. Because it's just the polynomial equation and it's just an algebraic equation. So these are operators. These are also product of operators. Then this P of T minus lambda is invertible, is equivalent to saying T minus lambda I is invertible for all I. Of course, if it is invertible for all I, then that is invertible. You can take the, you can flip, I mean, you can reverse the product and take the inverse. That will be the inverse of that. So if this is, on the other hand, if this is invertible, you fix one of them, one lambda I, you take all the other lambda i's and multiply that with that, that will be the inverse of it, right? It's clear, right? You can prove it in any ring. This is so okay. So this implies these two equation implies P of T lambda minus lambda is not invertible is equivalent to T minus lambda I is not invertible for some I. I mean, Pt minus lambda is not invertible, and this is not invertible for some I where lambda I, for some lambda I, where lambda I is the root of this equation. That's what this says. Okay. So now suppose you take this direction, P of T minus lambda is not invertible, so this is not invertible for this. This implies lambda I. So now let us start from here. P of T minus lambda is not invertible. This implies lambda I is in sigma of T for some I. For some I. And this is simply lambda is in sigma T means we know that P of lambda I is lambda because lambda is root of this equation. So P of lambda I is lambda. Okay. So this implies lambda is in P of sigma T. Lambda I is in this. We know that P of, I mean, which is always true because lambda is the root of the equation. So P of lambda I is equal to lambda, which is true always. Okay. Here we are proving that lambda is in sigma T. So this implies lambda is in P of sigma. On the other hand, lambda is in P of sigma T. Then, this original lambda is in P of sigma. Okay. I mean, this just says that lambda is equal to P of lambda I, and lambda I comes from there. That's what this says, right? So lambda is in P of sigma. Okay. Huh? This we have already proven for analytic function, right? Okay, yeah. So yeah, I didn't mind. Anyway, it's okay. Yeah, that's right. Only the other way we have to prove. That's what it is. So other way is also clear. The other way is suppose lambda I, so one of the lambda i's is P of lambda I equal to lambda for so one of the lambda i's. Then of course lambda I satisfies that equation. Okay, satisfies that equation. So that is not, I mean, this is not invertible one of them. P minus lambda is not invertible where lambda is lambda is the root of this polynomial. That is a Pt minus lambda is not invertible. So other way is also true. Okay. So proposition is true. Yeah, we proved earlier for analytic function we have this. Okay. So this is what is called spectral mapping theorem. I mean, there are several versions of this. This is for polynomial spectral mapping theorem. There is a continuous function spectral mapping theorem. Okay. So next we want to prove the following theorem. Proposition. Before that, we notice that let T is self-adjoint. Let T will be up. Okay. Then sigma T is contained in R. So T is self-adjoint is equivalent to saying Txx. I mean, Txx is in real. We know that we have proved this. We have proved this. Okay. So T self-adjoint. In particular, T is normal. So lambda is in sigma T is an approximate eigenvalue. May not be an eigenvalue, but since it is normal, everything in the spectrum is an approximate eigenvalue. Okay. So there exists sequence Xn contained in the unit ball. I call this H1, okay? H1 equal to this. From here onwards. Okay. Such that T minus lambda Xn goes to 0. Right? Is this the definition used? Right? This is the definition of approximate eigenvalue. Or did we use norm or something? I think we used we use norm, right? This is what we use, sorry. T minus lambda Xn. This goes to 0. This is what we use. Okay. Okay. Sorry. This is what we use. Okay. In particular, this is okay. This T minus Xn. This, of course, is mod of this is less than or equal to, of course, this is true, no? T minus lambda Xn, this norm. Then that is norm 1. So this goes to 0 anyway. This is also true. Okay. Now this is equal to T Xn minus lambda Xn is just lambda. Equal to this. That's what this is, right? These are all real. I mean, T minus lambda Xn goes to 0. Okay. So Txn minus lambda Xn. Lambda is a scalar. Lambda Xn is just lambda. It's a unit, yeah, Xn is a unit vector. Okay. So Txn goes to lambda. And this is real for self-adjoint operator. When T is self-adjoint. So this implies lambda is 0. So lambda is in sigma T implies lambda is real for self-adjoint operator. Okay. I mean, if it is an eigenvalue, it's easy to prove when it's direct. That's what you will prove when it's an eigenvalue. Here we use the fact that it's an approximate eigenvalue. Okay. So now we do the next proposition. Let T is self-adjoint. T equal to T star. T is self-adjoint and P is a polynomial. I mean, single variable polynomial with complex coefficient positive. Okay. Then norm of P of t, which is an operator, is same as you take the polynomial, restrict to sigma of t, which is a function, okay, which is a continuous function, right? And take its infinite norm. We define the infinite norm, no? Supremum norm. Okay? Supremum norm, we denote it by infinite norm. This is okay. This is what the notation I use. No? Okay? If you have a function, I mean, if I f in c of x, any c of x, then norm f infinity is supremum of f mod f of t. Okay? This is supremum norm. So you take the polynomial, consider it as a function on the spectrum sigma t, which is a compact polynomial is a general function, but you can consider it as a function of sigma t. Take its infinite norm. That is same as the norm of P of. That is the proposition. Okay. So norm of P of t square equal to norm of P of t star P of t. No, that's no problem. I'm thinking there is a subtlety about this being self-adjoint. I don't remember what is that. Self-adjoint operator, this is direct anyway. So P of t equal to Pt star Pt, which is equal to why I am considering this, I'm not sure. So this will have real coefficient, and this will have this is a normal operator. This is equal to the spectral radius of Pt star Pt, right? Okay, which is, you call it as, I mean, P bar P equal to Q. Let's call it. This is again polynomial. This is real coefficient, and that is equal to, I mean, this is just range of Q of spectral radius of Q of T. But then spectral mapping theorem says that this is equal to Q of, I mean, which is equal to supremum of mod of P, where P is in spectrum of Q of T, okay? Which is same as supremum of mod of P. The spectral mapping theorem, this is same as Q of sigma T. Now this is equal to supremum of mod of Q of P, where T is in sigma T. Same thing written in mod of, I mean, supremum of, maybe you can change it, yes or something. I mean, T in Q of sigma T, I mean, which is same as saying mod of Q of S in sigma T. So this is nothing but norm of Q infinity. It is just P bar P, which is equal to norm of P, I mean, norm of Q infinity, Q restricted to sigma of P, okay? Which is same as P restricted to sigma P square infinity. I don't remember why I consider only self-adjoint, not general norm. So now it looks like it will work for general normal operator also. I will think about this. For a general, if you take a general normal operator, okay, you don't need this. You can, I mean, this proof is okay. This is okay. This proves this. Okay? The norm of P of t is same as infinity norm of this polynomial restricted to sigma t. So if we take a general normal operator, that's also the spectral radius of that normal operator. And that is the supremum of this, something coming from that. and that is polynomial of that. The same proof will work, I think. So if we take any normal operator, I think this is true. Okay. Huh? Yeah. In the case of normal. Yeah. A normal operator, P of t and P of t star will commute. Yeah, there is no problem. I mean, you can have polynomials in Z, Z bar. Even that will commute, right? All of them will commute. So all P of t is also normal. In fact, you can take any polynomial in T and T star, and you can talk about P of t, T star. Polynomial in Z, Z star. Two variable polynomial in Z and Z, sorry, Z and Z bar. You can take a polynomial in Z, Z bar, P of Z, Z bar, and you can insert T, T star there. Okay? This will also be normal because T and T star commutes, right? Anyway, we'll come back to this. So let's define the C-star algebra. So A is a C-star algebra. It's a Banach algebra with an involution. Star from A to A. Satisfying, involution satisfies all the property of the adjoint, which is lambda x plus y star plus lambda bar x star plus y star. Okay. X y star is y star x star and x star star is x. Okay. And further, this is the crucial thing. Norm of x star x is equal to norm x. This is, I mean, we have seen this for operators. Operator satisfies this equality. So this is what is called C star identity. So C star algebra is a Banach algebra with another structure called involution. So there may be Banach algebra with an involution, but it may not satisfy the C star identity. Okay. So if it satisfies the C star identity, then we know that if norm of x star x equal to norm x square, then norm x equal to norm x star. We have proved it. Okay. But then there are Banach algebras where you can, you can have a star involution, but it may not satisfy this. That, for example, we will not go into it. For example, if you take matrices, and if you, instead of Hilbert space, if you take a Banach space, and you take the same adjoint as involution, then that will not satisfy the C star identity. L1 will not satisfy the C star identity. Okay? So, yeah, we've used for operator. It will follow here also, right? Norm x square equal to norm x square equal to norm x star x. Okay. So is it equal to norm x star? I mean, which is less than or equal to norm x star norm x norm x norm star. Okay. Yeah. Then we use, yeah. Then we use what? Yeah. So norm x is less than or equal to norm x star. And if you use the x star star is the norm x star is less than or equal to norm x. Okay? It's because of that. This implies norm x is less than or equal to norm x star. And the other way is also true. Yeah, because of that. So if C star identity is satisfied, then norm of x and x star is same, which will not be satisfied in other Banach algebra with an involution. L1. So examples of C star algebras are, I mean, these are the examples we will work with. P of h, with the usual, with the adjoint operators, or C of x, with f going to f bar. This is the star operation. Okay? And the star operation in B of h is adjoint, and C of x we will have just the bar, or we will take L infinity of h. Here also f going to f bar. This is the star operation. These are the three C star algebras we will work with, or we will work with any A contained in B of h, which is norm closed and satisfying T in A implies C star is in. It's closed under the star operation. Okay. So T is there, T star is there. It's closed under the star operation, and it's a star which is called star algebra. Okay. A star algebra, star subalgebra. Okay. Subalgebra means it's closed under all algebraic operation, addition and multiplication, scalar multiplication. So star closed means the adjoint is also there. So we take any such thing. That's also a C star. It of course it will satisfy the C star identity. So if S is any subset of B of H, any subset, then we can talk about C star S, the C star algebra generated by this. Which is usually, I mean, the usual definition, which will be the intersection of all C star algebras containing S, and which is the smallest C star algebra containing S. And that is indeed, this is the smallest C star algebra. Algebra containing S, which is same as you take all sorts of products and sum of this. Take all the algebra. That will be an algebra. Then you close it under. That's all. Okay? But when one, so this you can do it for a single operator. Incidentally, we will only consider unital C star algebras in this course. So T contained in B of H. Then you can talk about C star T, and let me put one also. I mean, it may not be the case, one is there. So it's a C star algebra generated by T and 1. Okay? T is normal. Then this is just, you take all polynomials in T and T star. Okay? And then take the closure in the norm. Of course, you take the C star algebra generated by T and 1. So it contains all the constants and it contains all the polynomials in T and T star. And there's and this way is clear. And to prove this way, I mean, this is a C star algebra. This is smaller C star algebra. This is just, you have something T, you have T star also there. And you only the product you have to worry about. Since T and T star commute, you will again get a single polynomial. I mean, polynomial T and T star. That P is, I mean, this is all those P of Z bar. Polynomials and Z and Z bar. complex polynomial in two variables z and z bar. Okay. Is okay, no? So C-star algebra generated by a normal element is, I mean, we always consider unital C-star algebra. So C-star algebra generated by a normal element. You take all polynomials and T star, just close it in a norm. Okay, that is the C-star algebra generated. Now make the definition. A representation of a C-star algebra. Of course, we use only unital C-star algebra. Okay, I will not say it again and again. Unital C-star algebra is just a homomorphism, is a star homomorphism, is a unital star homomorphism phi from A to some B of H, okay, for some Hilbert space H. That's all. That is phi of 1 is 1. This 1 is in the C-star algebra, this 1 is in B of H. Phi of 1 is 1. Okay. This is in A and this is in C-star B of H. Okay. Or I will write it as phi of 1A equal to 1H. Okay. This is the identity operator of H. Okay. And the pi of x star, this is a star in the C-star algebra, which is same as this is adjoint operator, pi of x star. And pi of xy is equal to pi of x, pi of y. And further, pi is linear. Okay. So it's just a star homomorphism. It preserves the star, it preserves the product, it preserves the, of course, linear structure. So this is what is called a representation. And we are not imposing any continuity condition because it automatically follows. Okay. So this is the remark. In fact, any homomorphism between C-star algebra, it contracts. Any star homomorphism. Say from A to B, both are unital C-star algebra. Is any unital, let's take unital. Okay. Any unital star homomorphism between two C-star algebra is contractive. That is norm of phi of x is less than or equal to norm of. Of course, if it is isomorphism, if it is bijection, then it will be automatically in isometric, non-preserving. Proof. So here we are taking the range C-star algebra to be B of x. Here this is true for any C-star algebra. Any C-star algebra homomorphism, star homomorphism is contractive. So norm of P of x square we want to consider, okay, which is equal to P of x star P of x, is the C-star identity. And that is equal to, because it's a homomorphism, that is equal to P of x star x. Okay. Notice that if x star is self-adjoint, P of x star x is also self-adjoint, okay, because it preserves the star. So this is self-adjoint. In particular, this is normal. Okay. So, and this is equal to spectral radius of P of x star x. Okay. Notice what? If x is invertible, P of x is also invertible. Right? If x is invertible, P of x is also invertible. So spectrum of P of x is contained in spectrum of x, right? It is unital, so it will take lambda to lambda. So if x minus lambda is invertible, P of x minus lambda is also invertible. So that implies not invertibility is the other, right? This is correct, no? Is right. If P of x minus lambda is not invertible, then x minus lambda is not invertible. Okay? So it is this way. So because of this, this is less than or equal to R of x star x. which is equal to norm x star x square equal to norm x square. Okay. So phi of x is less than or equal to norm x. Okay. And we use the fact that spectral, use the inverse, of course, it preserves the inverse, and we use the spectral radius is equal to the norm of that for a normal element, for a self-adjoint element. So, it is linear, of course. So this implies what? So corollary is, of course. So what does it say? Any contractive. So, this just implies that norm of phi is less than, as an operator, is less than or equal to 1. So phi is in particular, phi is bounded. Okay. So phi is bounded. So any homomorphism of system algebra is automatically continuous. Okay. Okay. So now I erased it here. I want to use the proposition which I proved here. The norm of some self-adjoint operator. What did I prove? Norm of P of a self-adjoint operator is the polynomial. It's the norm of the polynomial restricted to that spectrum. Okay. So I want to use that. So for that, I use the following. I prove the following proposition. That T is self-adjoint. Okay. T in B of H and T is self-adjoint. We'll shift between sister algebra and operators, but mostly we'll discuss with operators. T is a self-adjoint operator. Okay. Then there exists a unique homomorphism, or it's a representation of T of sigma T, okay, on H. For representation, we need a Hilbert space and of course, and a function. A map from the C-star algebra, homomorphism from the C-star algebra to B of H. So that's what we call as the representation on. Okay. I forgot to say something. I will say it. Sorry. What does it mean? What do I mean by uniqueness? No, this is okay. Here we don't need. I will define it later. I will define it in the next one. Here we don't need. So here the representation is unique. Is a unique representation of P of sigma T on H satisfying. So unique representation phi from sigma T to P of H, okay, satisfying phi of this function f naught equal to T, where f naught is the polynomial, single variable polynomial, f of T equal to T, f naught T equal to T. Okay. This polynomial, so this is all continuous function, okay, which contains polynomials. You take this polynomial, that polynomial will go to T. Okay. And this is the unique test. Okay. I'm sure all of you have done Sohn-Weierstrass theorem. Sohn-Weierstrass theorem, you have done already. In your BSc, you must have done. So, okay. So it is just use of that. First, we notice the T self-adjoint. So we proved we have so you define what we do is the following. So we want this to happen. Notice that once pi of f naught equal to T, okay, then pi of any polynomial is just P of T, right? And polynomials are dense here. Okay. And the map is fixed. Pi is clearly, provided it is continuous, it's clearly determined. So we have to prove it's continuous. And notice that any homomorphism of a C-star algebra is continuous. That doesn't mean anything defined on dense subspace is continuous. You have to prove it's continuous. I mean, it can be unbounded. Okay? This only says when it is defined on the whole of whole C-star algebra, then it is continuous. That's what that says. Okay? We can't use that. Okay? So if we define, define pi from C of, pi of f naught equal to f naught, and pi of any polynomial p is equal to p of, equal to p of t. Okay. Then norm of pi of t, okay, which is equal to, which is just the polynomial, infinity norm of the polynomial, norm of p. Norm of p. P is a polynomial which is on sigma t, right? Norm of p infinity is equal to norm of p of t. We have proved this. Norm of p of t. We have proved this. So this is an isometry. It's norm-preserving. In particular, it's uniform, continuous, or whatever. So you can extend to the closure, right? I mean, polynomials are dense. Polynomials are dense in C of sigma t. On each polynomial, on f naught, it is pi of f naught equal to t. Pi of any polynomial will become p of t. Okay? Since polynomials are dense, this is just a linear map. I mean, there is no, it will be automatically a homomorphism if you define on polynomial. Okay? So, because when you define it this way, okay, then it's defined on all polynomials, which is a dense subspace, and it is norm-preserving. In particular, it is uniformly continuous, so you can extend it to the closure. So, pi extends to C of sigma. Yeah. And that will be still a homomorphism. I mean, you have to see that that's still a homomorphism. Because multiplication is continuous, star is continuous, and all that. Because others will follow. Okay. You can verify. Should I do that? It's clear, no? Star is a continuous map. T going to T star is non-preserving. Star is a continuous map. So if you extend it, it will still be star preserving. And multiplication is a continuous map with respect to norm. It is jointly continuous. So it will still, it's still a it preserves the multiplication. It will be still a homomorphism. This is a homomorphism, right? Pi of f naught, you define it to be p. Pi of any polynomial is p of p. Okay. If you have two polynomials pq, pi of pq is p times q. Here also it is p of t, it's just algebraic relation. So it's clearly multiplicative. Okay. And that multiplicative property will be extended to the closure because multiplication is continuous and star is continuous. Okay. And pi of 1, of course, pi of f naught is t means, and you define pi of 1 as 1. Constant is 1. Sorry. Additionally, you define it. And constant, it is 1. So using these two conditions, you extend it. Okay. And this condition, pi of f naught equal to t, and it's unital, we are assuming it's unital also. This determines the homomorphism. So it's a unique extension, unique homomorphism, which satisfies this condition. So it's clear. Clear? No? Yeah. So given any self-adjoint operator, we have a star homomorphism between the continuous functions on the spectrum to B of H. Now, definition, two representations, pi 1 from A to B of H1, and pi 2 from A to B of H2 are unitarily equivalent if there exists a unitary operator U from H1 to H2 such that unitary operator satisfying. So I bring U star, it will be here. So pi 1 of X, then apply U, that will go there, which is equal to pi 2 of X. Okay. This is what is called unitarily equivalent. There is some thing called quasi-equivalence is there, but we will not use that. We will use only this unitary. Okay, this is enough for our purpose. So it's like they are same. I mean, unitary operator. If you have a unitary operator between two Hilbert space, which will preserve the inner product, which is a bijection. Okay, so that means that there you can treat them as same Hilbert space. Similarly, if you have a unitary operator between them and you have two representations, then you can treat them as same representation. There is really no difference. Okay, so this is you identify the two representations. So that's the purpose of this definition. So we do the following proposition. This proposition uses the Riesz representation theorem. I will state it. So it is supposed to have been done in Ghana 1, but since you have not done, you can look at some book or I will post a video. Okay, so this is theorem. Riesz representation theorem. This is for more general for complex measure, which just says that you take the continuous function. I mean, for a metric space, X is a metric space. We will be dealing with something in C. Okay, I mean, we will be usually dealing with sigma of some P. So it will be a compact subset of C, or maybe in Cn at some point. So it's all metric spaces. So X is a metric space. It just says C of X star. C of X star, the dual of C of X, is just says that, I will write it again, I didn't write it what we want, the statement we want, is all complex measures. Complex measure, if you have a measure, see, if you have a measure which is defined on from omega to P, you have a measure, okay, then this mu of omega will be like a norm for this measure. You can add measures, right? Of course, if you assume complex measures, okay, you can add this measure. But then this will not be, this will be a complex number for complex measures. So if you have a mu, there is something called, I mean, this is not, we don't need it, I'm just stating it. If we need it, I have to do it. Let me see whether we need it. So if you have a complex measure, you can define you can associate a positive measure to that, which is what is called total variation measure, which is not just the mod of that. I mean, that if you have, let me just define it. If complex measure is just a additive function on the sigma algebra. Okay? It's like measure. Okay, it's not. It can be. You can apply. I mean, it can be. It can take values complex values. But the nice thing about it, it will take. It will not. Of course, it will take values in complex number. It cannot take. You cannot allow infinity. Usually, measure you will allow infinity. Infinity is not a real number, so you will allow it. But here it will take in complex numbers. So if you have a mu, is a complex number. Is a complex measure on omega, then you can talk about mod mu, which is mod mu of any set E is equal to supremum of, let me write it, summation mod mu of, this mod is mod of the complex number, okay, mod of mu of EI, where E is equal to disjoint union of E, E equal to 1 to N. Okay. You partition this E disjointly, then you take all this summation. This is the usually total variation is defined for functions and other things. Okay, for differential total variation is, this is how it is defined. Okay. You take the all partition and take the supremum of this. This will be a measure. You can prove that this is a positive measure, which is a slightly long proof. Okay, so you can define this is a positive measure, and this mu going to mu. Now a complex measure is a vector space. You can multiply with a scalar, complex scalar. Any measure can be multiplied with a scalar, you will get another measure. Right? The same additivity, everything will be preserved. You can add two measures. Signed measure itself is enough, that will be real vector space, this will be complex vector. Signed measure is taking values in real line. It need not be positive. Okay? So a complex measure is a vector space. Okay? And the norm will be this mod mu, which is a number, mod mu, mu going to mod mu. This is the total variation measure. This is the mod of the total variation measure of the whole set. That will be a norm. So the Riesz representation theorem says that C of x star is just complex measures in the following association. So C of x star is all complex measures on, which is usually defined by m of x, all complex measures. Of course, this is just a association. How it involves is, if you have a mu, a complex measure in x, then you can define a linear functional pi mu from x to c by, as you know, f going to, sorry, not x, c of x, c of x to mu c by pi mu of f is equal to integral f d mu. Like you integrate with respect to any measure, you can integrate with respect to complex measure also, which is direct. You can, there is a theorem, which is again you have to prove. If you have a complex number, you can decompose into 4 positive measures. I mean, you can decompose into real part and imaginary part, that's okay. But then any signed measure or real measure, you can write it at mu plus minus mu minus, 2 positive measures. I mean, these are all one has to go through. So once you do all that, any fee, you can write it like that. You can define the integration, and once you know the integration with the positive measures, you can define for complex measures. Okay. So this is how the association is. The statement I need is the following. I only need for positive functions. So in Riesz representation, that is what is proved first. Then using that, the general statement is proved. So definition. P is a linear functional from A to C. It's a linear functional. Of course, from here onwards, always A is a unital C star. Unital C star. Is positive, is said to be positive. That means we call it a positive linear function. Okay, if P of any positive element is positive, that is P of x star x. I didn't say what is positive element. Okay, let me just say, forget about what is positive element. Any phi of x star x is greater than or equal. That's all. Okay, let's not worry about this definition. We will come to this later. We are not going to use it, but I'm only using it for the C star algebra. C star algebra. I mean, for C of x, this just is phi of mod f. I mean, any f star f is mod f. Any positive, phi of f is greater than or equal to 0 for all f greater than or equal. If you have a positive function taking values in the positive real line, that's what is a positive linear function. That's what a positive, then it will look like x star x, no? You can write it as f bar f, right? F bar f square root or whatever. Okay? So if you have a positive function, positive linear functionals on C of x are those which satisfies this condition. P of x is greater than 0 if f is greater than. So the Riesz representation theorem is the following. If let phi from C of x to C is positive, it's a complex linear functional. Yeah. Here. Positive. Huh? P is a linear functional. Linear function. P in. Actually, if it is positive, it will be automatically bounded. So I will not get into this. Okay. So I mean, we'll talk about it later. Okay. So for C of x, I think P of 1 is 1. It's based on. Anyway, for yeah, if it is positive, then norm phi is equal to P of 1. Okay. So anyway, for C of x, this is the definition. It takes positive function. We don't need all that. What we need is the following. For C of x, if you have a positive linear function, P of any positive function is positive. Okay. Then it's positive. Then there exists a positive finite measure on x such that P of f equal to integral f d over. Okay. That's all. So every positive linear functional is given by positive measures. Then you can prove that every linear functional, complex linear, bounded complex linear functional is actually given by that. And further, if you want to compute the norm of f, that will be mu of whole omega. That's clear. Right. How that is clear is P of 1 is that. You have to prove that norm is equal to P of 1 or not. Anyway. But this is the only statement I'm going to use now. Okay. Let T equal to T star. T is a self-vector. That's it. Okay, maybe I'll stop. It will take some 10-15 minutes, this theorem. So we'll do it tomorrow.